So for A7, you're basically implementing steer to center, which is essentially line by line this algorithm. And the difficult part is not figuring out what the algorithm is, but how do you actually get each of these values, and what do they mean within the context of each engine, and things like that. I shared with you a simulation that I made to show you what each of the values should be in each case, and I'll explain that right now. So I have this simulation. So in this simulation, you are the camera. So this is a camera. It would represent your head. The red bounds are essentially the guardian, or whatever you call. I guess in the Vive, it's just called the tracking area. Whatever. This is your physical space that you can walk in, and in this simulation, you have a couple of options that I'll explain in a little bit. But the basic idea is that if I want to walk to this green cube, in real life I would be stuck. You know, these red bounds are the physical space, so imagine that I'm walking into a real life wall. I need some way of getting to that cube without hitting the wall, so that's why we do redirected walking. So if I were to rotate towards the center, say that a distractor or something appeared, then my entire physical space would rotate under a threshold that I wouldn't notice, and then I can walk into the green cube. There's also a translational gain. As you can see, the entire tracking space is shifting a little bit as I walk, because in VR you feel like you're walking very slowly if you don't do any kind of translational gain. So I'll explain this in a little bit. But let me just explain what these values mean. So d and angle between vectors are just two general purpose functions. These two values here, previous forward vector and previous yaw, they are initialized here so that nothing happens in the first frame. And so each frame, these values are calculated. First, there's how much the user actually rotated. I'm going to decrease the frequency of my simulation so that it takes a while for the redirection to actually get applied. So if I rotate very quickly, you could see that how much user rotated is a very high value. If I don't rotate at all, it's a pretty small value. So that's what that is. Notice that it's always positive, which is why we need to figure out the direction. So direction that the user rotated is given by D. If you look at this little, this green and blue thing, you'll see that D is basically a classifier. It just tells you if you rotated left or right relative to the previous frame. I'm going to make my simulation run faster. So yeah, what D is in this current frame is highlighted. Next you have delta yaw relative to center. That's a kind of confusing name, but I don't know what else to call it. It's essentially the signed difference between the yellow and blue vectors. So if I decrease the frequency of my simulation, if the yellow vector, so this is the center of the physical space and I'm looking this way. If the yellow vector is closer to the origin than the blue vector, that means that I'm rotating towards the center, which means that I should accelerate towards the center, which means my threshold is higher. If the yellow vector is farther from the center than the blue one, then that means that I'm looking away from the center. So hopefully that makes sense. And remember that the reason we need to accelerate or decelerate is that we can accelerate. So if I'm already rotating towards the center, and the whole point of our of steer to center is to rotate somebody towards the center, we can accelerate somebody very easily in that direction and it won't be very noticeable. But it's a lot more noticeable if you are rotating against their head, because the person will, at some point they'll pick up on the fact that you're doing counter rotations. What is next? Distance from center is pretty self-explanatory. It's this pink vector. It's just it's just the distance from the center. The reason we need to calculate that is basically when, let me decrease the simulation frequency or increase it. So the reason we need to know the distance is because if the user is already in the center, then you should not rotate any, you pretty much shouldn't rotate at all because they're already in the center. They're already at the position that gives them the most walkable space in any direction, so there's no need to rotate them. But if they're very close to the bounds, we want to rotate them as quickly as possible. See? At the moment, it's pretty much just a linear function where the distortion increases the farther that you get from the center. It's probably more appropriate to think of the bounds as a circle because of this. Longest dimension of the physical space, you can basically just hard-code it. I hard-coded it as 5 meters down here, and that's the size of these red bounds. You can get that information from the VR API, but the problem is that with certain devices like the Oculus, you can draw very strangely shaped guardians, and in Unreal or Unity, they essentially, those dimensions that you get approximate that thing that you drew as a square, and sometimes you don't know if that square is a good approximation or how it's oriented or anything like that. So it's sufficient to just hard code it. What else? The how much to accelerate part. That is just, it's just it has all of the things that we just calculated as a factor, and it's the actual amount of rotation that you apply. As for how you apply the rotation, in Unity you have this rotate around vector. Whoops, typo. You have this rotate around vector, function, which will just rotate you around a point. In Unreal, we need to use a pivot. The reason that which position you rotate around is important is, let me disable all the unnecessary stuff. So I'm going to pause this. I have this pivot, and every frame I'm essentially parenting the VR player to the pivot and then rotating the pivot by some amount. Right now the pivot is at the camera location, right? And so if I rotate the pivot, my user won't move, because we're only for steer to center, apart from translational gain, we don't really want to translate the user. So if we pivot around their head, then no translation happens. If we were to pivot around something else, like the center, so for example, if you just rotated around the center, here's the problem. Remember that your VR character is essentially the entire tracking space, and the tracking space's origin will just be in the center of the space somewhere. So if you rotate around that point, the user does translate, and in fact, the farther they are from the center, the more that they'll translate. And this will have a similar sickening effect that that joystick motion has. So the person will feel that they're being translated against their will, and they'll start feeling simulation sickness, or motion sickness, or whatever you would technically call it. So that's why where you pivot actually does matter, and we need to put some thought into it. What else? In my simulation, oh god. In my simulation, you can do a couple of things. So 9 and 0 will essentially change the amount of frames that you wait before finally applying the rotational distortion and translational gain. As for translational gain, as you can see, the red bounds move when I move. If translational gain is basically, if it's basically disabled, where if the threshold is 0, then that means that when I walk, the space will not translate. if I make it a very high value, in real life, it would feel like I'm walking on ice. I don't know what that slow rotation is caused by. It's some rounding error in my code. If your gain threshold is really high, then you'll feel like you're walking on ice. But you do walk very fast in the virtual, in the game. If you hit 1, you can induce random rotations, like head rotation. In real life, we wouldn't actually be this jittery, but there is a decent amount of randomized head rotation. Just that, not quite at this frequency. It's more like drift or swaying in real life. Although with eye rotation, you do actually get this kind of randomness. What else? As for what to submit, you can hit 2 to remove all of the unnecessary things that I added here just as a visual aid. So when you submit a 7 as a non-VR user, you can basically just submit this. So you have the position of your camera, basically, and something that indicates its direction. So you can add a cone like I did. And you also want to have the bounds so that I can actually tell that the rotation is happening. So the bounds you can add by simply parenting a cube, a furry flattened cube under the physical tracking space center. That it means that it's following the entire tracking space, and since you're rotating and translating the tracking space itself, that's why the bounds will follow it. So yeah, if you're doing this in VR, then the submission instructions haven't changed. So that's all I can think of. Good luck, and you can DM me in Discord if you need help or during office hours. Bye.